Okay, here's our last example looking at shear and moment diagrams. Slightly more complex example. So here we have a beam with a roller and a pin. It has a distributed load and then two forces. So the first thing we're going to do is start off with full body analysis because we need to find FA from the roller and FB from the pin. Our distributed load is the area, so base times height. That gives us 900 pounds at a total of 7 feet. So now we've found our FA we need to find our FA and FB, and we're gonna do that by pinning the beam at point A and then taking the sum of the moments about that point. So we start off with 250 pounds caused counterclockwise, so positive 250 times 4 feet minus 900 times 3 feet plus FB times 6 feet minus 250 times 10 feet. So that tells us that FB is 700 pounds. Now that we found FB, we can solve for FA simply by some of the forces in the y direction. So FA plus FB minus 900 minus 250 minus 250, and FA is also 700. So now we found our full body diagram, or full body. We know all of the forces. So now we're going to move on to finding shear, and we're going to use the graphical method here because it's a lot simpler than the mathematical method. When you start having all of these distributed loads, graphical method is the way to go. Okay, so if we start at point 0, at 0 feet, there's a 250 pound force going downward. So at 0, we're at negative 250. Then from 250, right, from x equals 0 all the way to 4 feet, we have no other force being exerted besides this 250 here. So we stay from 0 to 4 at a constant negative 250, right? So we're at a constant negative 250, and then all of a sudden at 4 feet, we have this 700 pound force pushing us upward. So whenever we have a force applied, all of a sudden we have to jump. So we jump from negative 250 plus 700, we jump up to 450. Alright, so we've jumped. Now what we need to do is take into account this distributed load. So the distributed load is going to take us from 4 feet to a total of 10 feet. So let's see here. What we have to do is we know that we're at 450 up here. What we want to find is our end point at 10 feet. And how we find that is by finding the area under the distributed load. So base times height, so 150, but it's downward, so it's negative 150 times 6. That gives us negative 900. So this tells us that at point 10, what we have to do to find the end point is our starting point, so we're at 450, subtract or take away this 900, so 450 minus 900 equals negative 450. So we know our starting point is 450, our ending point will be negative 450. How do we know whether we're going to be constant, linear, or parabolic? Well, because the distributed load is this constant line, this constant load, we know that our shear is going to be linear. Okay, so from here, we're at 10, we're at negative 450. But all of a sudden, at 10 feet, there's another 700 pound force upward. So even though we're at negative 450, all of a sudden we have a jump upward plus 700 pounds. So negative 450 plus 700 brings us up to 250 pounds. So we're at 250, and once again, this last 4 feet, there is no force being applied up until the very end. So we just stay at a constant 250 until the very end at 14 feet. And this 250 downward brings us down to 0. So this is what our shear diagram will look like. The most important thing is realize what is your starting point. So realize what your starting point is, find what your ending point is based on your shear or based on your distributed load, and then use your relationships of constant to linear to parabolic to determine what that section of the graph will look like. So now that we found our shear, we're going to use the shear diagram to determine the moment diagram. So starting at 0, there is no moment being applied because this is a beam with a roller and a pin. If there was a wall here, then we would have some moment, but there's no wall, it's just free floating. So our moment is 0. Now we need to find our end point. We find our end point by finding the area under the shear curve. So negative 250 times 4, that gives us negative 1000. So from 0, we end up at negative 1000, and we know that this portion is going to be linear because the shear diagram is constant. So if this is constant, then this becomes 1 power higher, so this is going to be linear. From here, we know our start point now is negative 1000. How can we find our end point at 7? So all we have to do is find the area under the curve here. So it's a triangle 1/2 base times height. That's 675 pounds times feet. So negative 1000 plus 675 brings us up to negative 325. So we know our starting point, we know our ending point. How do we know whether this is constant, linear, or parabolic? Well, because this under the shear curve is linear, this must be parabolic. And in order to determine what your parabola will look like, just think of it like this. As you move from 4 to 7 feet, the area under your shear curve is getting progressively smaller. So the same thing must happen for your moment curve. The area all of a sudden is really large here, but then it gets progressively smaller. So whatever happens to this area must also happen to this area. So for the next portion, we know that our starting point is negative 325. We take the area under this curve now, and that's negative 675. So starting point, negative 325, minus 675, so our ending point is negative 1000. And once again, we know because this is linear, this must be parabolic. And the area under this curve is getting progressively larger, so the area under this curve must also get progressively larger, and that's how we know that the parabola looks like this. And then for our final portion, we know that we're at negative 1000 here, and we want to figure out where we would be at 14, so we find the area under the shear curve, which is 250 times 4 feet, so that's 1000. So negative 1000 plus 1000 tells us that at 14 we're at 0 pounds per feet. And we know that because this portion here in the shear curve is constant, that this must be linear. So this is what our final answer looks like, and let's run through it real quick. So from 0 to 4, we have only one force being applied. So that means that our shear curve is going to be constant. But then from 4 to 10, we have a distributed load. So whenever we have a distributed load, which is constantly being applied for every foot, then our shear is linear. And then in the end, we have no force being applied until the very end, so our shear is constant. Looking at shear to moment, our shear here is constant, so our moment is linear. Our shear here is linear, so our moment is parabolic. Our shear is constant, so our moment is linear. And this is a very, very good example, and it kind of touches on pretty much everything that you need to know on how to use the area from a distributed load to get to shear, and then the area from the shear to get to moment.